Very good, thank you. Hey, so I'm going to be speaking about IP deployment strategies, mainly focusing on the SMPTE-2110 deployments. So here's what we'll be covering: the types of traffic, just in general for IP networks, approaches to PTP distribution, because that's something that people have nightmares about now, and there are logical and optimal ways of distributing PTP across a network. Multicast and architectural considerations to take into account when you're putting together your system, followed by some bandwidth management strategies, and just conclusions afterwards. So everything I'm going to be talking about is really just strategic, because the worst thing that can happen for a broadcaster is to see this on the air. We never want to see black on the air. That's really bad, and people lose money and people lose jobs, and we don't want to have that happen. We'd rather keep high quality programming like this on the air. One of them is a bit better than the other. I'm not going to say which. So first, let's talk about the different types of traffic in a network. So there's broadcast, which means one packet goes to every single device in the subnet. That's broadcast. Unicast traffic is just one-to-one, always one-to-one, one source to one receiver. And then there's multicast, which can be one-to-one or one-to-many. And the sender sends something, and then one receiver or a series of receivers request that. Multicast is really good fit for uncompressed media deployments and television market in general, because a lot of times people want to replace traditional SDI routers, bare metal SDI routers, with an IP fabric. And this is really helpful because, like a traditional SDI router where you can send bars to every single multi-viewer, you can do the same thing in the IP world. Send one source, one multicast source, to every destination or any destination you want. The sender doesn't need to know where you're actually sending it to. That's up to the receiver to actually decide if you want to consume that multicast feed or not. And multicast is kind of, I have found it's kind of niche almost. Media folks like us, we use it every day. Financial institutions, they use it every day, whether for trading and things like that. But if you talk to many IT departments, even at really large broadcasting companies, just the IT departments, they have no idea what multicast is. So this is a really great opportunity for broadcasters to learn this technology, learn these protocols, and really be able to be at the forefront of this and work with the IT departments in communication and developing new system upgrades. So let's talk about PTP. Again, this is scary. A lot of people do not like this, but this PTP is distributed in networks today. SMPTE-2110 is not theory anymore. There are many active deployments all over the world, both 24/7 facilities and mobile trucks. They're all using it. They all have they all have strong PTP deployments. So let's review some of those. So what is PTP and how does it work? PTP is really just timing for your SMPTE-2110 devices. Generally, we're talking about SMPTE 2059-2. That just means that certain messages that I'll talk about in the next couple slides, they just have different rates, different frequencies. And there are different profiles. So there's something called 2059-2. There's also one called AES 67, IEEE 1588. There's different types of profiles that are used. Generally, we use one domain in per network, per profile, I suppose. That pretty much just means that one grandmaster that will feed every slave device in the network. And obviously, PTP is absolutely vital for SMPTE-2110 networks. Without it, some devices just won't turn on or won't produce any video. You'll be out of sync, and we never want to see that happen. So what is PTP from a networking perspective? PTP is multicast. It is 224.0.1.129. Every single message in PTP is 224.0.1.129. So does this abide by the regular standard rules of multicast routing? The answer is yes, but there are caveats to this, things that we want to avoid. So in multicast, if many sources have the same multicast destination feed and you request that, you will actually receive every single one of those. And that's where we'll get into in a couple slides. So there are different types of messages in PTP. There's an announce message, which is used by the slaves to elect an actual grandmaster in your network. This has all the attributes in there that are used to elect the best one. Then there are sync messages and possibly follow-up messages. These are what actually contain the time in the messages that go to the actual slave devices. And then there's delay requests, which are sent back from the slave to the grandmaster. And then there's a delay response, which is sent back from the master to that slave. These are important because these are used to help calculate the one-way delay, just so your timing can be absolutely 100% as accurate as possible. As we know, timing needs to be accurate in a television facility. So these are all the different types of messages, again, and the frequencies that we typically send them at. So we send one announce message once a second. Sync and follow-ups might be 8 messages a second. Delay requests and delay responses are also possibly 8 messages per second. So if we have a total of 300 slaves in your system, which is relatively small right now, you can see that the slave device, propagating through the network, there might be 7,500 messages per second. That can be important for different PTP modes and how much processing goes on in the switch itself. But the slave messages transmitted per second, that would be 2,400 messages per second. That can actually be really damaging if you don't select the correct PTP mode. Because remember, they are all 2,400 of those per second are all 224.0.1.129. That means every single slave device would be seeing every single one of those 2,400 messages a second. And that can, again, be really damaging for not just the slave devices, which might not be able to handle all that traffic, but the grandmaster itself may not be able to handle that traffic. As an example, an SPG, a Tektronix SPG 8000A, can, I think, handle about 1,024 devices without the use of what's called a boundary clock. Just because it can handle that doesn't mean you really want to. So we try to avoid inundating a slave device with this many messages. Also, it just causes extra jitter. And we never want to have jitter in the network. We want it to be as solid as possible. So with all these messages that are floating around the network, there must be a way to actually prevent this from damaging the network, or a way to just prevent these messages from really propagating at all. So for that, we're going to be looking at the different PTP clock types. So there's a boundary clock and a transparent clock. Boundary clock is pretty much where all PTP messages go to be suppressed. So every slave device that's going to be sending out all of its 8 messages per second, once it hits that interface that it's connected to, they will not go anywhere. They go straight to the CPU, and that's it. They will not propagate through the entire network. And that's really good, just because that really cuts down on all of your traffic. Boundary clock mode is recommended in almost any environment. You can also run each interface at a specific rate that you want. So you can say on a specific interface, I want to have 4 announce messages per second. And then on another one, you can say, I want only 1 message per second. So it's pretty flexible in that way as well. And also with boundary clock, if you were to lose connection to a grandmaster, again like an SPG 8000A, if that were to be lost, then the switch would operate in free run, or it would be free run, but it would be a holdover time for a fixed amount of seconds. By default, that's 28,800 seconds, so around 8 hours. So you would actually maintain that time that was previously on the grandmaster, and it'll be extremely accurate for that 8 hours. And another benefit of boundary clock is also security. So in any boundary clock switch, you should be able to set every interface to say, I only want this to be a master interface. What that means is that any device that's connected to that interface cannot essentially be the grandmaster of your system. That's also really important because you wouldn't want to have someone connect in, I don't know, a microphone into the system with higher priorities and then have that be the grandmaster of the system. You just wouldn't want to do that. So this is just an added measure of security. And then there's also transparent clock. Transparent clock can eliminate jitter really by calculating the propagation time within the switch. So how long a packet actually spends in the switch and then correcting it on the outbound to the slave interface, which with a correction field. So if it spends 6 microseconds in a switch for whatever reason, it'll actually add that amount of time into the time that it sends to the switch. Both have their advantages, and both have their place in any PTP network. In transparent clock, because the messages don't get suppressed, unlike in boundary clock, you can operate hopefully slave devices in what's called hybrid mode. Hybrid mode means I want to receive everything in multicast, essentially, but for the delay request messages, I'm going to send them back as unicast to the actual grandmaster. That means that the slave devices, all the delay requests, won't be going to every single other slave in the network. They will only be going back to that grandmaster. So that's something else that we can take advantage of. So back to the BMCA, which stands for Best Master Clock Algorithm. These are the attributes that are contained in the announce message that assist with the election of a grandmaster. There's priority 1, there's clock class, so GPS equals 6 and free run equals 248, and different variations between there have different numerical values as well. Clock accuracy, clock variance, so the jitter, priority 2, and the MAC address. The two, priority 1 and priority 2, are highlighted because those are actually configurable in any device, including the switches, and you'd want to take advantage of these configurable fields so that you can pretty much choose who's going to be the grandmaster under any circumstance. And by the way, the order here that they're in is the order in which they're elected as well. Like, those are the attributes. So if something has the best priority 1, no matter what everything else is below it, that will always be the elected grandmaster of the system. So PTP, so controlling who is your grandmaster. So in this scenario here, would anyone like to venture a guess? Who is the grandmaster of this overall network? I'm going to pick on Al Karloff. I know your name. Right, and why is that? Correct. So look at that green check mark go with an explanation. So the P1s have the same value, which is great. They're both clock class 6, so they're both locked to GPS, but their P2, as Al said, the P2 for GM1 is a lower value, therefore it's elected grandmaster. So now in this case, GM1 lost its GPS. Who is elected grandmaster in this case? Bill Hoskins. Yeah, who's going to be the grandmaster for this system? Right. That's because P1s are still identical, but GM2 is locked to GPS, therefore it is the preferred grandmaster for the system. How about this one, where you lose both grandmasters because maintenance decided to power them off because they didn't think they were necessary? Possible. Who would be the grandmaster in this case? Just call it out. Sorry? Yeah. Follows the same rules as the first one before, GM1 and GM2. So yeah, in this case it is switch 1. How about this one, where the connection is severed between the two switches? Who is elected grandmaster here? Right. There will be 2 grandmasters, one for each network, because there's no connection, so they won't be able to communicate who is the actual grandmaster. So there will be 2 grandmasters in the system, which could be really damaging, especially in this case where GM1 has also lost its GPS. So both sides might be totally different in terms of their timing. It is possible, or if not necessarily losing its GPS, but just powered off as well. You don't want to have 2 grandmasters, 2 different time sources in your network. That's just recipe for disaster. So this is what a real PTP distribution network can look like here. You've got multiple switches connected together, operating in different modes. So if we notice, the M there, that stands for master, the S stands for slave. We notice here that we have boundaries connected to boundaries, and then boundary connected to other transparent or boundary switches. Those are really good. So in this case here, with all the control ones in the bottom switch, all of those PTP messages will not be seen at every other host. They will go into that switch and they will die. Same with all the other boundary clock switches. Now, the reason why on this transparent clock you don't have an M and an S on that directly is because that clock, that switch, doesn't actually know who the grandmaster is. In that case, it's really just multicast traffic. So it does not care. It just passes the traffic to its, in this case, its CCU, which is the slave in that case. And one final note for PTP, invest in PTP monitoring. It's very important. You don't just want to have to learn that there's something wrong by devices blinking, by video blinking or audio going away or anything like that, or relying on someone in the networking department to just happen to log into a switch and do a show PTP command. Invest in PTP monitoring. There are lots of companies that do this. We do this as well. With Cloud Vision Portal, we have a PTP monitoring app. It is very useful for obtaining all necessary PTP statistics. Any questions on PTP in any way? Yeah, 8 hours, except there's a possibility, for 8 hours, and that's configurable. But, so are you saying that it's okay to lose a grandmaster?
No, I'm not saying that. You wouldn't go ahead.
You could if it's left for long enough. I don't know. I'd rather be in a facility with a real grandmaster instead of relying on any switch, which is nowhere near as accurate as either a Tektronix or a Meinberg or whoever. But you're right. Like it will. That's the beauty of boundary clock. But what happens also if you don't operate in boundary clock? What happens if you're in transparent mode, where that isn't taken, where that switch will not maintain its accurate timing? So, all right. So let's now go into multicast and some architectural considerations. Really, we have to know all of our endpoints when we're designing the network. Do they support source-specific multicast, or do they not? If they don't, then you need what's called a rendezvous point to route multicast traffic. And when I'm talking about routing multicast traffic, I mean routing it from one subnet to a different subnet. That's just like how you would do routing in a unicast environment. It can operate in the same way, just in multicast. So routing from one subnet to another subnet. Source-specific multicast means I want to request 239.1.1.1 from 192.168.1.10, for example. If it doesn't support source-specific multicast routing, that means I'm going to say I want to request 239.1.1.1 from whoever has that. So I don't know who has that. And in that case where I don't know who has it, I need to use what's called a rendezvous point, which is just something that's configurable in any and all of the switches that we would provide. I generally put this in anyway, a rendezvous point, just in case later on down the road someone adds a device that doesn't happen to support SSM. Really, it's a safety precaution. I'd rather make the changes. I'd rather do all these configurations before the system's online than while it's actually online. And if it does use SSM, source-specific multicast routing, then the rendezvous point will not be used. But if it doesn't use it, then it will be used. So it's pretty advantageous in that case. Knowing your PTP distribution network. Will boundary clock or transparent clock be implemented, or both? And avoid non-PTP aware switches, pretty please. Never have a network with non-PTP aware switches. They are really they can be really difficult and really time consuming to configure. I'm dealing with customers even now who select certain brands of switches that don't have features for PTP in 2110 networks because they didn't think they mattered. It's important. for your timing. It's very important. With non-PTP aware switches, you can get extra jitter, and some devices are less tolerant to that than others. And obviously know your switch platforms. Are you going to be using 10 gig or 25 gig or 40 or 100 or even 400 gig, which is released in Q3 of this year. So we can have spine switches with all 400 gig interfaces, a lot of them. Or you can have chassis switches with 400 gig blades in them, a lot of them. Like those are huge, just a huge amount of traffic. Think about all the, ultra, UHDs of keeping up with the Kardashians that you can put on there. It's huge. And then obviously know your feature sets, whether or not you want deep buffer switches. For 2110 systems, we generally recommend that. The PTP clock modes, and also, if they all support FEC, which are, some switches do not. And we've seen issues with other vendors where because they don't and endpoints require FEC, there is incompatibility there. So always know your feature sets, always know it, and research it before you ever take into account, before you ever, purchase these switches, obviously. So let's do an architectural overview now of Layer 2 Multicast. Layer 2 Multicast can be deployed with SMPTE-2110. I'd recommend it for certain deployments, but not all, especially when there's more than one switch involved. That's because of uncontrollable multicast flooding. So in any VLAN, there's something that's called an IGMP querier. What this means is pretty much it is an address in the switch that sends out a query message to every single receiver in that subnet, asking it, what multicast address do you want? And that happens every 125 seconds, okay? By default, multicast in layer 2 floods to the querier. So in this case here, where we have two switches, and they're both in, say, VLAN 100, all the cameras that are on switch 1 in VLAN 100 will flood over to over the connection between the two switches, over to switch 2, because that is the querier. That can obviously be very damaging if you're talking about 4K cameras or anything. If you have 3 cameras that are spitting out 10 gigabits per second and you only have 2 10 gig links there, you're going to kill your pipe there. So that's really not beneficial. So cascading switches in layer 2 can really be damaging. And then also with layer 2 multicast, in the absence of an IGMP querier for that VLAN, multicast traffic floods every interface in that VLAN. So in this case here, let's pretend I have a querier on switch 2, but I don't have one on switch 1. And I were to lose the link between the two switches. All the multicast traffic on switch 1 in that VLAN, VLAN 100, would flood every other interface in that VLAN. And obviously, again, that will not be healthy in any way. Also in layer 2 multicast, there's another pitfall. These 3 cameras are spitting out multicast addresses of 239.111, 238.111, and 237.1.1.1. Those are unique, right? They all seem unique to me from an IP perspective, and they are. The problem with that is in a layer 2 environment, we don't care about the multicast address. We care about the MAC address. And unfortunately, so every single multicast address does correspond to a MAC address, but they're not unique. For every single multicast MAC address, there are 32 corresponding multicast IP addresses. So in this case, these all 239.111, 238.111, and 237.111 are all the exact same MAC address. It's very disappointing. That means when the monitor decides to request just one of those, just 239.111, it will receive all 3 signals, even though they are unique from an IP perspective. That is clearly not a good thing for every reason I've already brought up where you can oversubscribe your link. So there must be a way to kind of suppress this and fix this, and the answer is, and there is. It's using layer 3. So having layer 3 connections between the two switches. That would be very helpful. And so in order to do that, we just set 2 IP addresses, one on each switch, have them directly connected, and probably use some type of routing protocol. This is beneficial because in this case here, the 3 cameras will not go from switch 1 to switch 2 unless they are actually requested. That's why a lot of any scalable multicast network will be using layer 3 instead of layer 2. And you can go as far down in layer 3 as you want. You can have different VLANs on the same switch. All the interfaces on that one switch be in, all in VLAN 100, or you can go even further and say, I want every single interface to be a routed interface, a layer 3 interface. We've seen customers do both. Both work just fine. So these is obviously also far more scalable. I still wouldn't necessarily recommend cascading switches in this type of environment, but you can create, but you can definitely create more scalable systems when you use layer 3. Also, you're really reducing your blast radius in this case. So if we go back to the other example here, if one of those cameras happens to malfunction and just starts broadcasting out, it'll impact the signal, it'll impact both switches. Whereas in this case, if one of the cameras happens to be malfunctioning and broadcasting out to .255, I guess, or just the packet is just not created correctly, it will only affect what's on that local switch, on that local VLAN, on that local switch. So you're really reducing your blast radius when you, or your failure domain when you're taking advantage of layer 3 multicast. So options, things to think about. How do we decide how resilient we want the network to be? So will we be using SMPTE-2110-7? What topology are we going to want to use? Monolithic or an IP fabric? Will we be using layer 2 or layer 3 multicast? The answer should always be layer 3. If the networks will be a red and blue, air-gapped, or will there be purple networks? And will we want to use a broadcast controller that's bandwidth aware, or will we just want to rely on IGMP protocols to say what multicast address do you want, and then renew that every 125 seconds or so? These are all choices we have to make. So this is what a monolithic solution could possibly look like. You have 2 7504 switches, 2 chassis switches, and all your endpoints are probably connected to both of them for SMPTE 2022-7 redundancy. Now I consider these to be air-gapped even though there is a connection between the 2 switches. I only allow PTP to go between the 2 switches, and the reason for that is in the event that say a primary link on one of the switches dies and it can only get its data from the secondary link, I still want it to get the primary clock on the left-hand side. That's why I allow PTP to go between both switches. And you can put in access lists, you can put in multicast boundaries. There's various forms of security you can put in there to prevent any other multicast traffic or any other traffic really from going between those 2 switches other than the desired PTP traffic. So this is obviously pretty simple because you can put everything in one VLAN if you want. You can separate them by line card. You can do whatever you want. The configuration is relatively simple, as you don't really require routing protocols for this because everything would be directly connected. But obviously, scalability has to be well thought out if you're going to go with a chassis switch like this. You don't want to have be 95% full on every single one of your interfaces on that switch before you ever go to air. That would not be beneficial. You don't want to have to rip these apart and buy new, larger chassis switches before your on-air date. So you really want to think this through and figure out where am I going to, where am I now, where am I going to be going to, and what type of traffic will I be using? Because right now, maybe you're using HD at 1.5 gigabits per second. And you can have 4 interfaces broken out on one 40 gig interface on the line card. But then, every time, if you decide you want to go into more UHD with 40 or 100 gig interfaces, you lose the density there because then you obviously can't break that out unless you're using 400 gig line cards. So you really have to think this through. And, if you do properly, this can really just be the beginnings of a of an IP fabric where you have leaf switches hanging off of this, which would be acting as a acting as a spine switch, acting as a core switch, which we get to here. So these can also come in handy, especially if you have equipment rooms, in different equipment rooms scattered throughout the building and different endpoints scattered throughout an entire building as well, and you don't want to run individual strands of fiber, like tons of fiber throughout the entire building. You can just focus on running, your 100 gigs or your 400 gigs, and multiplexing all the traffic onto that one cable. So this is obviously very advantageous as well because the scalability factor really is there. You can scale by just expanding east to west and not impact all the other leaf switches. So provided that you leave the proper number of line cards, the right number of interfaces, how many interfaces you need connected from each spine to each leaf, you can really have a very, very, very scalable network here that can expand almost anytime. You can just pop in another leaf switch, connect that to the spine, and you're off and running. There are some possible things you would need to add into your network when you go in this direction, though. So in this drawing, I have it shown where it's one connection from each leaf to each spine. But in reality, you'd probably have more than one connection. You'd probably have maybe 3, maybe 4 connections. Who knows? So routing protocols are not aware, really. So you may have to rely on control systems that are bandwidth aware, which we'll be getting into shortly later on in this presentation. And then there's another IP fabric like this. Really, it's very similar to the one before, except instead of being just red and blue, it's called the middle switch there is a purple switch, which has both the primary and the secondaries connected to it. These really come in handy for devices that are single-homed, possibly like an embryonics SFP, for example, where you may want to be able to get signals from either a primary or a secondary side at any point. So in that case, it might be considered connected to what's called a purple switch, or a microphone, or any other device that's single-homed. So now let's talk about bandwidth management. So this really comes into play when we're dealing with the IP fabric, so the core and then the various leaf switches that are hanging off of that core with multiple links between them. So the routing protocols like IGMP, PIM, those are not bandwidth aware. So you never know for certain if there's multiple links there, which multicast flow will go over which link. So you're leaving it up to you're leaving it up to various hashing algorithms to determine for you which link I want to go up. And again, it's not bandwidth aware. So there is the possibility that exists where all the traffic will not be evenly distributed throughout the various connections. And that can be a problem because at some point you may run into a situation where you're sending a UHD signal up one link and it's 99% full or something like that. And that's what push it over the limit, and then you would lose you would lose every other signal on that stream, on that connection, pardon me. So for some of these, for a bandwidth management system, you don't even necessarily need these routing protocols because the controller would be bandwidth aware and be able to look at all the links and then automatically for you place the multicast signals across the links which are less saturated than others. This can open up opportunities for the bandwidth controller to actually be quicker than relying on standard routing protocols than standard PIM or IGMP. You could possibly do things actually quicker if all the methods are implemented correctly. So there is something that Arista produces, which is called Arista MCS, Media Control Service, which does this for you. So Arista MCS is not a broadcast controller on its own. You need a partner, such as an Imagine or a Lavo or a Grass Valley or some other control system, to integrate, to talk to the Arista MCS, and then from there, the Arista MCS will talk to all of the switches, and for you, it'll route the multicast traffic across all of the switches because it is bandwidth aware. So this is really important to know because it just provides the availability to have a bandwidth management system and not rely on the routing protocols. But again, it's important. Again, I'm just going to stress this again. Arista MCS is not a controller on its own. It needs it is just an intermediary between your standard broadcast controller and your networking switches. So who would need something like MCS? So large distributed multi-switch systems, multi-switch topologies, where oversubscription is not necessarily is a possibility, not just in terms of, if you have 400 gigs allocated or allotted, but you only have 200 gigs, but just any time you have a whole whack of traffic that's possibly going over all of those links. That's when you really might need and want something like this. You wouldn't necessarily need it on a monolithic switch though, because obviously all the traffic stays within that one chassis. If it doesn't leave the chassis to go to other leaf switches, you don't necessarily need it. Although you could use something like that in the event that you wanted faster routes to take place. Because again, we still have the benefit of being able to route multicast traffic quicker through an Arista MCS than relying on the protocols themselves. So single switch deployments might not need this, but IP fabrics, hub and spoke, those types of deployments, they really might need something like this that is bandwidth aware. But if you don't want to actually use something that's, if you don't want to have an intermediary between the broadcast controller and the switches, we actually offer something else. Our switches are relatively open, are extremely open. That's what we pride ourselves on. It's a Linux OS, and you can do whatever you want almost with the switch. So we also support what's called OpenConfig, which is a vendor-neutral, model-driven protocol that allows for all the data to be streamed from the switches to your controller or your NMS or whatever, and it also allows you to very, very quickly adjust the configurations on the switches themselves. So in this case, you can have a broadcast controller that will actually talk directly to the Arista switch and not need an Arista MCS. It'll be able to talk to the switch directly and be able to ascertain from the bandwidth that is available on the links, route the multicast traffic across a series of links, going from a leaf to a spine to another leaf. So these are just some of the companies that are using and driving OpenConfig. The protocol that's used for OpenConfig is called gRPC, which was developed by a small company called Google. They really demand that this get used by all of their network vendors. And again, this is a list of just some of the companies that are using it. Very large companies, very influential companies, and we would, it'd be great if broadcast vendors as well developed code to speak to the switches in this way also. And Arista switches speak this way already using gRPC because that's how we get all of our telemetry data to CloudVision Portal, which is our NMS to monitor all of the switches. So it's already supported on every single platform. So if you're using the Arista switches for media, so live or play out, or whether you're using it for file and storage, and you want to be able to obtain telemetry quicker, the OpenConfig is supported on every single one. So you could even write this in-house if you wanted to. Suhail could write this in-house if you wanted to. From what? Oh, Python? Well, with this, it's just the connection, I think, is just a bidirectional connection. It uses any programming language in there. Sorry. So how does this apply to the media networks? Again, it's a standardized model. So if every switch in the world supported OpenConfig, then a broadcast controller that also supports OpenConfig could talk to any switch in the world and perform the exact same functions. You have very high performance of read and write read and write capabilities, and for very fast programming and streaming of all of your telemetry data. So you can really get your counters very quickly. You can see LLD, like neighborship, so when interfaces go up and when they go down, you'll get notified very quickly. You don't have to rely on constantly polling the Arista switch for all of the statistics. They just will be getting streamed from a client to a server. So to conclude, obviously there are many considerations to take into account when you're designing a network for SMPTE-2110. You have to consider the topology. You have to consider your PTP. You have to your PTP distribution network. You have to take into account all the feature sets that you will need now and in the future, and really just think about not what you want to get out of it now, but later on as well. Even there's going to be signals that are 40 gigabits per second coming out soon. So we even are thinking about those and really planning into the future as well. And IP really has extreme flexibility. You can really scale out your network if you design it correctly, very easily, and that's something that really should be taken advantage of for any live production deployment. And if you have any questions, you can find me after. I want to thank everybody for listening to my presentation.